Welcome everyone to the ITC lunch. We have a record crowd today for an obvious reason. Not every week we establish a new area in astrophysics, and that's quite remarkable. It's not just a new frontier, but also a new messenger that we're using to learn about objects in the universe. Gravitational waves are being used for astrophysics. In other words, they were detected from a source that has matter in it. And so that's a very rich phenomenology, and we will hear about it in the first half hour of this lunch. There were 4,000 authors on more than 60 papers on the archive on Monday night, which was quite remarkable to watch. I was on none of these, even though they included most of the observers in the world, actually, most of the astronomer observers. And so it's quite remarkable, and it's also remarkable that the details were kept confidential with so many authors involved. I mean, the idea was known, but not the details. And the other thing about this particular event is that Forbes magazine estimated that there were 100 Earth masses worth of gold produced in it, which is worth 10 to the power 28 dollars. That's but much more important than that is the information that we will hear about in a few minutes. We just heard an excellent ITC colloquium by Avishai Dekel, who is visiting us today and tomorrow, and he will speak a little later. We will start with 4 presentations related to GW 170817. It's easy to remember this number. First by Hsin-Yu Chen, who is a postdoc fellow at the Black Hole Initiative, and she's a member of the LIGO collaboration. We will talk about the gravitational wave signal that was detected, and then we'll hear about the electromagnetic counterpart that was detected by members of the LIGO-Virgo's group here. And they include Matt Nicholl, Phil Cowperthwaite, and Kate Alexander. So the first talk will be 8 minutes, and then 666, and then we'll have time for questions. That will be the first half hour, and then we get to our standard 4 presentations in ITC luncheons. So this forum will continue until 2 p.m. instead of 1:30 as usual. And the other 4 presentations are by Avishai, who will speak about the origin of ultra-diffuse galaxies. And then we'll hear from Dan Hooker, the CFA colloquium today, visiting us from Fermilab. And he will talk about HAWC, Pulsars, and the Positron excess. Then we'll hear from Richard Bauer from Durham University, who is somewhere here. Has a beautiful accent. And he will tell us about the impact of Lambda. And finally, we'll hear from Lluis from Oslo. Where is Lluis? Over there. And he will tell us about very interesting results on the diffuse emission halos as a probe of galaxy and reionization physics. We'll start with Hsin-Yu.
Okay. Well, hi everyone, Hsin-Yu. I still feel very not real to put these 2 plots in same slide in my title slide. So I'm a member of LIGO and also a member of this dark energy camera discovery, which is one of the independent team that discovered the Kilanova. We discovered this truly golden binary neutron star mergers, GW 170817. It is golden not only in the sense that it produces lots of gold. It's truly a golden in many sense. It's a spectacular event. And it was spectacular that the first one become something like this. So I remember September 21st, same luncheon here, I put up these slides of kind of a long list of the science we try to achieve with this binary neutron star multi-messenger astronomy. And it was very nice to see that all these lists are at least either check or we have some sense of all of them just with single event. So let's start with this golden binary. This is strongly my point of view. Why we call it a very golden? What really lead to this wealth of science afterward? It's because of two reasons. First of all, it is very close. And given a very close binary, that is actually almost 2 to 3 times stronger signal than our LIGO detection threshold. We are able to measure all the relevant parameters very well. And another good things about this, how close it is that if it is further away, let's say more than 2 times further away, then Fermi wouldn't detect the short gamma ray burst from this event. So that's one thing, the distance. Second thing is the localization of this event. So for this event, if we only have a LIGO detector, the 2 detectors, we're only able to localize the event into the light blue region. So you see 2 big arcs. However, there's another interesting fact, which is that at the same time, the Virgo detector was already on, and it is sensitive to a certain level. So, but we didn't see any signal from the Virgo, which is it got to be some reason because this event is very close, it's very loud in the other 2 detectors. If you want to expect something that's totally non-detection or very weak detection in the third, the Virgo detector, then the most likely reason is that the event lie at the blind spot of the detector. So for the gravitational wave detector, we are almost isotropic to the sky, but we do have 4 different blind spots relative to the detector. And the fact that Virgo didn't see it indicate that it lies at one of these blind spots. And that's why in the end, we have a very well localized down to 28 square degrees on the sky. And that leads to the very good discovery for the following EM counterpart. So in these slides, all these green underlying title are the title of all the papers put out by LIGOs. I try to summarize them in the following. So the first one is our discovery. And then after our discovery, we have this multi-messenger observation for all these different bands. The observer captured the short gamma ray burst and also their afterglow in X-ray and maybe in radio as well. And another type of EM counterpart is the Kilanova. So we got both for this very first event. Just showing a beautiful picture for dark energy camera. Dark energy camera is one of the independent team and sent out this Kilanova discovery rapidly so that we can have follow-up observation. I'll leave this to the later talk. And another good advantage for that cam is that we cover 80% of the LIGO's localization area so that we can make sure there's nothing else, there's not other candidate lie within the LIGO candidate, and this is the one. Okay, so what we can do with all these discovery first, with EM observation, we have the Kilanova, we identify the host galaxies, then we have the redshift of the host galaxy. So that's a redshift. From LIGO side, we have the luminosity distance estimation, and that directly lead to this measurement of the Hubble constant. This is entirely an independent way of measuring the Hubble constant, independent of all of this distance ladder. And this is what we found. So this is a Hubble constant constraint. It has about 15% uncertainty, center at and consistent with all these previous found Planck value and the value found from supernova. They are consistent. Another interesting but more astrophysical quantity we constrain from this signal is the inclination of the binary. So so how we measure the inclination and why is that related? So it is because the signal strength of this gravitational signal is actually related. It is decided by the distance. So you can you can imagine the strength goes inversely as the distance. But also the binary, if they are phased on the gravitational signal, it turns out to be stronger. So this leads to a degeneracy between the distance and inclination. We have some constraint. But given the existence of the NGC 4993, the host galaxy, we got some constraint of the distance. And therefore, we can go back and constrain the inclination of this binary better. Or you can play the game the other way around. If you got the inclination from EM side, then you will come back, restrict the distance better, and therefore the Hubble constant better. That's one of the paper put up by Dekel and Berger's group 2 days or yesterday. Okay, there are other things we can talk about. There is this short gamma ray burst emission. It is consistent in time and location. And we can start to talk about, say, the consistency of the gravitational wave speed to the speed of light. We can also talk about why this short gamma ray burst is relatively dim. Is it because the jet of the GRB have some structure, or we are totally off the jet of the GRB? There's some discussion and some theory being developed here. We can also talk about the progenitor of this bineutron star merger, just from the fact that the projected distance of the binary neutron star merger is only 2 kiloparsec from the host galaxy. Then we can try to reconstruct the history. When was the things formed? Where was it formed? There is also search of the neutrino high energy particles. There was no detection. But with LIGO side only, we already can, just with our data, we can also say something about the Kilanova. That's 8 minutes? Okay, so let me just try to wrap up. We can say something about the ejecta mass, and it was consistent with the EM observation. It can account for the heavy element amount. We also try to look for how much it's going to contribute to stochastic background just from the rate. And we have a lot more paper in preparation from LIGO side. So I guess, well, all I want to say is that there are a lot we can still talk about, and we would like to hold this, maybe start this journal club or some LIGO science related discussion. So if you're interested, please email me, and we just had our first meeting yesterday, and we would like to continue it maybe in a weekly or twice a week base, and we can talk. Thanks. I think that's a plan. We will have it in the BHI. Yeah. Thanks.
Okay. All right. So I'm Phil Cowperthwaite. I'm a grad student here in Berger's group, and I'm going to talk about light curves and the actual modeling of this event. So Hsin-Yu is talking about, we have this whole zoo of counterparts that we want to consider. So we have a short gamma ray burst, which is Fermi and integral SAW. If you launch a short GRB, you should have a jet, so maybe you have an on and off-axis afterglow. So you could imagine having counterparts in optical, X-ray, or radio. And then the one that we really want to talk about is the Kilanova, which is this isotropic near-infrared emission. It's much like a supernova, but instead of being powered by Nicholl 56, it's instead powered by the radioactive decay of our process elements synthesized in the ejecta. So just a quick description of our data set that went into this. So the source was identified really rapidly within 12 hours. So we're able to get a lot of data. I think people have compiled it. There's something like 600 and some photometric data points that were released in relation to this event. Personally, we have U through Y band optical imaging with Dekel from about 12 hours to roughly 14 days. We have a single HST epoch at plus 10 days, and then near-infrared photometry from Gemini South in H and KS band out to almost 20 days. So if you put all this together, you get this, which is our light curve of Kilanova. So there's a lot of really spectacular features in this event. So first of all, if you look at something like U band, you go from 17 and change to almost 22nd magnitude in a few days. It's like a decline rate of 2 magnitudes per night. It's really incredible. And G band is not far behind. You can see out to it's shortly longer lived in each band as you get redder out through I, Z, Y, H, and then still detectable out in K to almost 18.5 days. And really the only reason these observations stop is because the object was so close to the sun, there's basically no more time at the beginning of the night to really observe it sufficiently, or much more constrained by that than the actual brightness of the source. And then you can just look at independent, to get rid of all this clutter, you can look at different bands. So here's G band, quickly declines and becomes not detected. I band lasts a little bit longer, then H band really almost plateaus through early times and then starts to decline. So we want to fit this with the model. So what do we expect for Kilanova? So this is from Dan Kaysen and Brian Metzger. Shows various starting scenarios. You either have 2 neutron stars or a neutron star and a black hole. That leaves various remnant scenarios where you have a hypermassive neutron star form, but it only lives for a short time, maybe 100 milliseconds, and then collapses to a black hole. Maybe that hypermassive neutron star was rotationally supportive and just lives forever, or at least much longer than the event that we're looking at. Maybe we just get a prompt collapse to a black hole, or a prompt collapse to a rapidly spinning black hole. So each of these have different rough expectations for what you expect for a Kilanova, but in general, they all have roughly the same features, which is some sort of blue emission and some sort of red emission. And that basically comes from, depending on your exact remnant scenario, the composition and the electron fraction of your ejecta can change both as a function of position and time, so that you either produce a lot of our process elements, which give you sort of the classic very red Kilanova that people talked about many years ago, or if you have less our process production, then you have maybe closer to iron opacities, and then you have a blue Kilanova. So we wanted to fit this, so we used sort of modified Arnett law model that was adapted by Ashley Villar here to work on Kilanova. We fit this model using James's MOSFET code that James and Matt worked on to perform an MCMC fit to the multiband light curve data, which is great because it's a lot of data that we want to fit. And sort of the key parameters that we consider are the nuclear heating, so we have our process heating in our model. We have ejecta mass and velocity, so we have 2 components. We have this red and this blue. We just see how they interact, so we fit the mass and velocity of each independently, and then we treat it with a gray opacity. So fitting that, you get this, which is our sort of our best fit 2-component model. It's really nice. It does very well in through here, and it really captures a lot of this Z-band and Y-band structure. It has roughly the right shape, as the red component takes longer because it's lower velocity. So as the blue component fades, that red velocity ramps up, and you get this hump. Has some other interesting things that it doesn't hit. So it overshoots the H-band, likely due to an absorption feature in the spectra that's just not accounted for in like these parametrized light curve models, and probably the same thing in K, where it slightly undershoots K initially. This hump was originally, I thought it was anomalous, but actually after looking at all the data that came out on Monday, everybody sees this sort of bright overshooting of K and then decaying back through here. So it does very well in G, does okay through I, has a little trouble here. This might be the photosphere going optically thin, so it declines more rapidly than the model predicts. And then, of course, H band. So this is very exciting. So the total is we produce about 5% of the solar mass of material. Has 2 distinct components, one moving about 0.3 C and the other at 0.1. This is nice because it's consistent with, say, early blackbody fits that people did many months ago. And we allowed the opacity of the red component to be a free parameter, and it very strongly fit to only 3 centimeters squared per gram, which is interesting because that's a sort of more of a moderate electron fraction, not really the heavy our process elements production that we expected. So we can comment on, real quick, lastly, heavy element production. So one of the big things that everyone talks about is production of gold, but really neutron stars are thought to be a really important source for most heavy element production, maybe half of the stuff above iron. And the ability of the neutron star to produce that material very strongly depends on its composition, and because you can see as the electron fraction of the material rises, that means it's less neutron rich, so it has a harder time producing heavy R-process elements. So for 0.1, you can get all the way out to an atomic number of hundreds. These are the actinides, and these are the lanthanides, these 2 red regions. If you have this more intermediate ejecta like we find, then you really only produce maybe out to the lanthanides. And then if it's much higher, you really only sort of get to iron peak. But the nice thing about this event is, we can work out all this later with more detailed modeling. But just a nice back-of-the-envelope calculation based on the rates, sort of the masses that you expect, and sort of the time is all consistent with binary neutron stars being nice dominant source of our process production in the galaxy. But of course, if you want to talk about what's actually in stuff, we should talk about spectra, which I'll leave to Matt. You want to just a dongle? Okay. Yes. Probably do want this.
I do want that. All right, so hopefully Hsin-Yu and Phil have convinced you that we find a Kilanova. Now I'd like to show you some spectra of this Kilanova. So this is the first time that we've ever observed spectroscopically the signature of a neutron star merger like this. So we really had very little idea what this would look like, but we got a ton of data, and now we have a pretty good idea. So first up, I'll apologize for the color scheme. This was made for public outreach, not for science. So this plot shows our optical spectrum and our infrared spectrum obtained from SOAR and Gemini, both in Chile. So this is 1.5 days after the merger. So as Phil said, 12 hours after this thing happened, we saw it in DCAM. The next night we started our spectroscopic observations. And we got spectra pretty much every night until it became too faint or too close to the sun to see anymore. So the first thing that jumps out is this really broad, obvious peak at around 5,000 angstroms, which is really very far to the blue end of what we ever thought we would see from a Kilanova. But it's detectable all the way down through the infrared, so you can see this red flux too. And what's really interesting is if I play, this is actually a movie, we let it run, you can see that by only one day after the first spectrum, most of the blue flux has disappeared, but the flux in the red stays much more constant. So this is kind of consistent with what Phil was saying. I think this is evidence of a two-component ejecta. So something powers the early blue flux, something else is powering the red flux, and these two things fade on very different timescales. So these are very nicely resolved at around 9,000 angstroms, which made it easy for optical near-infrared spectrographs to split this up. So let's look at the optical spectra first, and zoom in a little bit. So in a slightly nicer color scheme here, you can see the evolution again from 1.5 days, a broad peak at around 5,000 angstroms. The next night, the flux is shifted all the way over to 7,000 angstroms. And you've got this really sharp cutoff, which is very unusual. We typically, when we see a transient like this that we think is powered by some thermalization of radioactive decay inside an expanding photosphere, we think black body. But as you can see from the inset here, it really looks nothing like a black body, especially beyond the first night. But this cutoff of blue wavelength is so much sharper than you can get from the simple black body models. So we think that is indicative of these R-process opacities, these F-block elements especially. They have these really high force of absorption lines in the blue wavelength to just sort of terminate this flux below, say, around 7,000 angstroms here. We also got this ultraviolet spectrum, single epoch from Hubble, and the UV spectrum seems to be completely absorbed. So maybe actually some of you recognize the UV spectrum. It was the source of a bit of a headache for me. But I remember Avi enjoyed the Nature rumor article that came out because of it. So I wasn't sure if I was going to show this, but I like it because it's probably the highest controversy per photon of any observation in history. All right, back to science. That's my LIGO leaks joke. Okay, so as Phil mentioned, the physics behind the Kilanova is very similar to a supernova. You've got some radioactive decay, but our process rather than Nicholl. You've got some initially optically thick massive material that this energy is inside. So one thing that was natural to do was compare, well, how does the spectrum look compared to a supernova? And as you can see, completely different. Top panel is supernovae around their maximum brightness. Bottom panel is a supernova shortly after explosion. For a Kilanova, maximum brightness shortly after explosion are the same thing. Two things to note. The supernovae have the obvious resolved line features that the Kilanova does not have. And the supernova has this much bluer continuum that's far closer to thermal than the Kilanova. So together, those two things suggest that, first of all, the Kilanova composition is not oxygen or iron or things that supernovae are made of. It's these R-process, more complicated atomic structure elements. And secondly, that the velocities are extremely high, so all these lines are Doppler blended together, which is what gives this really smooth spectrum we see here. So as well as the light curves, we also modeled the spectra. So on the left, you can see a model for the optical spectrum. I will stress that these models were calculated actually before this Kilanova was ever discovered. These are just plotting our data versus literature models. provided by Dan Kaysen. So the fact that these look anything alike is pretty stunning to me. Theorists really did an incredible job with this. And over here, the infrared spectrum, we do even better. So in the infrared, the model actually matches both of these sort of two broad spectral features here, close to the correct wavelengths. So from these models, we infer some parameters about the ejecta. The most important one to note here is the lanthanide fraction. So we keep talking about this blue and red kilanova with different opacities, and the different opacities are dominated by the lanthanide fraction in the ejecta. So to match the IR spectrum, you really need something like 1% lanthanide in the ejecta. To match the optical, initially close to 0 in the outermost ejecta, and something like 10 to the minus 4 lanthanides by mass as the photosphere recedes into the deeper lying material. So that's actually pretty constraining for the composition of this material. And to match sort of the width of these absorption features here and the lack of features in the blue, the velocities have to come out to be about a third the speed of light for the blue kilanova and a little bit slower in the red, about 0.1 c. And these parameters we infer from the spectrum are actually incredibly close to what Phil just showed from the light curves. Two fairly independent ways of looking at this, one with complicated spectral models and one with very simple light curve models, but they come out almost exactly the same. So really this shows to us pretty convincingly you've got a separate blue component from fast, low lanthanide ejecta, and a redder component from slower, high lanthanide ejecta that's slightly more massive. So the source of those two components has some interesting implications. So currently we think there are 3 different ways to get ejecta. Okay, I'll go on for 1 more minute. That's okay. 3 different ways to get ejecta from the kilanova. In the polar direction, you can get material shocked from this collision or a disk wind. In the equatorial plane, you get tidal stripping. And the lanthanide fraction predicted is very different. In the polar direction, you've got more neutrinos, less heavy nuclear synthesis. So that's why you get the blue material there. To get high velocities in the polar direction, you really actually need the collision rather than the disk wind. And that suggests that both components of the binary were neutron stars rather than a neutron star in a black hole, which LIGO can't tell us by itself. Also, the mass of the polar material is kind of a function of the neutron star radius. The more compact neutron stars can get closer together. They hit at higher velocities and you get more material. So this actually can help us to start to think about the neutron star equation of state, which favors a more compact neutron star. And now I will stop. Thank you. And 6 minutes is short. Yes.
So I'm Kate Alexander. I guess I should.
Yes, you should. I knew I was going to do that.
All right, cool. So I'm a graduate student in Ito's group as well, and I'm going to talk about the other half of the EM follow-up we did in the X-ray and radio, where we detected evidence for a relativistic jet in addition to this kilanova. So Phil already showed this plot, so I won't belabor it too much, but I just wanted to point out that we really hit the jackpot here. We detected pretty much every single kind of EM counterpart that has been predicted for binary neutron star mergers. So I'm going to focus on the emission from this relativistic jet that was accelerated during the collision that produces a short gamma ray burst and also afterglow emission. If you are on axis, you'll see this very bright burst of gamma rays and very bright afterglow of X-ray all the way through radio. If you're off axis, initially this will all be relativistically beamed away from you, so you won't see anything at early times. But as the jet slows down and decelerates, interacting with the surrounding medium, you will eventually be able to see the afterglow, and it'll just peak at a delayed time. So if you see this peak come in at a later time, you can learn something about what angle you're viewing the system at. The afterglow emission is this very broadband synchrotron emission, which gives us a nice constraints on some of the key physical parameters of the system. So we can learn about the energy, the circummerger density, and then microphysical parameters of the shock front that is generated between the jet and the surrounding material. And as this nicely shows, we see the spectrum extends all the way from the radio through to the X-rays. So we should be able to see it in every band. The optical and near IR for binary neutron star mergers, as we've heard, is dominated by the kilanova component. So if we want to look for this, we should look in both the radio and the X-rays, and the peak of this spectrum will shift toward lower frequencies and fade slowly with time. So we want to look early, except if we're off axis when it's beamed away from us and we won't see anything, but then we'll still want to keep checking back in because it will fade away. So first, we observed this event with Chandra and Swift. And at 2.5 days after the event, we don't see anything at the position of the optical Kilanova counterpart, which is the orange circle up there. But when we looked again, starting 10 days to 15 days later, we do see X-ray emission showing up. So this rising emission suggests that perhaps we are seeing an off-axis relativistic jet. And then a few days later, we also see emission show up in the radio. The host galaxy has a weak AGN in it, so this is a much brighter source of radio emission, but we do also detect faint radio emission from the host that starts to appear around this time. And this is 2 weeks after when everybody else had to stop observing because the source went behind the sun, but radio astronomers can keep observing in the day, so we're going to keep looking at this event, and in fact, we've been able to keep tracking it a lot longer than everyone else has. So previously, we've seen events like this before in the form of cosmological short gamma ray bursts, but those events were all seen on axis and were much, much brighter in the X-rays and the radio than this event that we see here. So this just shows a series of afterglow light curves for a selection of cosmological short gamma ray bursts in gray. And you can see that both the X-rays and the radio are many orders of magnitude fainter than this. So a standard on-axis relativistic jet is completely ruled out by our radio and X-ray observations, and in particular by the fact that they are rising with time. However, we do find that this is very consistent with typical parameters for the energy and the density seen if the jet is pointed away from us. So on the left, I have a series of models that show what you would expect for two different sets of typical parameters for various viewing angles. And these are some of our radio upper limits shown here. So you can see that the radio upper limits for a wide range of possible parameters rule out jets that are within 20, where the observer is viewing within 20 degrees of the angle down the jet axis. And you can see that the high energies are also ruled out for a much wider range of observer angles. So we basically made a grid of all of these simulations and went through and iterated until we found the parts of parameter space that match the data. So on the right here is one of our best fit models. We have the radio light curve in purple, the optical light curve in green, and the X-ray light curve in black at the bottom. And we see that for an energy of about 10 to the 49 ergs, a density of about 10 to the minus 3 particles per cubic centimeter, and a jet opening angle of about 15 degrees viewed at about 30 degrees off axis match the data pretty well. And the dotted or dashed line at the top there is roughly what the luminosity of the Kilanova that we observed is in R band. So we can see that the predicted emission from this off-axis GRB afterglow is many, many orders of magnitude less, so we're not seeing any contribution from this in the optical. And really our best constraints come from the radio and the X-ray. So since we are a little over time, I'll just stop there. But we have already constrained the viewing angle of the system. We confirmed that binary neutron star mergers do also produce these relativistic jets, as has been proposed for 10 years in the study of short gamma ray bursts. And we're going to keep monitoring this in the radio, because eventually the Kilanova ejecta, which is much slower, will slow down and decelerate and should also produce detectable radio emission, which will give us another chance to constrain properties like the density of the surrounding environment. And I'll point you to our website and to AppJ Letter's focus issue for more. Thanks.
No, the other connection.
Oh, are we ignoring you, Avi?
Sorry, just the question was finding these in just with traditional targeting. Yeah.
surveys of the sky and circle them and calibrate the rate without waiting for the next LIGO event. That's my focus. But
Yeah.
also for LIGO, given that you can restrain the angle of the information event, that can feed into the LIGO analysis.
Yeah, so a lot of things. So first of all, in terms of finding these in pre-existing surveys, that's actually quite difficult because the cadence of a supernova survey is actually still quite long compared to the time scale for this event. So I think people have done this in terms of looking back through IPTF data or CanStars. Yeah.
I'll also point out that we already have some idea that not all Kilanova look exactly the same.
Yeah.
So Wenfei Fong has done some searches in short GRB afterglows and done some follow-up at very late times as well to look for this delayed radio emission from the Kilanova, and also at early times to look for this optical emission. And a few events we're able to set limits on the Kilanova brightness that are much indicate there's a range of Kilanova luminosities.
Sure.
Yeah.
If you assume that this one is consistent with what you would see for everyone. So there could be viewing angle effects where you...
Sure.
Yeah.
Look for those that look like this.
Yeah, and I think there are some optical surveys that are planning to do that. ZTF has a nightly cadence, and they're planning to look for
exactly.
things like this. And I'm sure that a lot of people will be doing that going forward.
When will LIGO become operational so that we can
Next.
see more
In a year.
in a year? So during that year, you have plenty of time. Other questions? Yes.
I have a question. How big is the blind spot, the Virgo blind spot? Has the Virgo detected before able to control strand the source location better or worse?
So it really depends on several parameters, especially the inclination of the binary. From the LIGO only detection, we have some info on the inclination, but we cannot constrain it that well. So just to answer your question, it really depends on case by case.
It seems to me that this event is a much more constraining test of general relativity than any of the prior detections. Because in the prior detections, the mass and orientation of the objects were inferred from general relativity. Here we have an independent measure in many respects of general relativity. You sort of know the upper limit mass of the two objects because we understand neutron stars. You have some idea of the geometry, you know the distance. So I guess the question is, how close does the waveform, the gravitational waveform, conform to the best estimates of the geometry of the merger, the distance, and the masses of the wave?
That's actually a very interesting point of view, and we haven't done that study yet.
One thing that was done was trying to constrain the Hubble constant in 10% or so, and it's not given. Standard values, I think you reverse this, you would say that everything is not given. Now, most of the gravitational wave signal is actually inside. You're going to see the plant itself, because that's not the strong enough signal. What you see is the sort of post-Newtonian inspiral plant, which you measure hundreds of orbits, is it? Thousands of orbits coming slowly together, but it's not the actual plan, different from the two black holes.
So you say it's not a test of the strong gravitation.
I mean, you're not probing the furthest way like you do with black holes.
Constraint factor for lower Kilanova, but not the higher.
Last
It's
question.
better.
We have last question.
Been reported widely that the gamma ray burst was observed 2 seconds after the gravitation. Do we understand that 2 seconds?
It depends on your exact model. So to say we understand it, no, but I think there's a lot of ideas in terms of delayed jet formation or delayed breakout time because of all the ejected material. So there's a lot of theories that people are working through in terms of, if you don't have a prompt collapse to a black hole, it could take some time for the jet to launch. There's a lot of material there. It could take some time for the jet to break out of that material. And it was very low luminosity compared to most short GRBs. It was 10,000 times lower luminosity. So, because we're far off axis. But
Anything through the speed through the medium
No, I don't think it's been folded back into.
Well, it's a part of the Lorentz factor of the jet.
Yeah.
It's fine. Yes, so the jet that emits eventually is a bit slower than the emission if they were moving at the same speed, it will not. But since the jet is slower, it needs to find so there are constraints among the 60 papers that are due.
Sorry for that.
So I would like to congratulate you all for the beautiful results. It used to be the case that cosmology was a hottest thing, then it became exoplanets, and now it's clear that the signs for rotational elasticity.
So, great excitement. This is older excitement. So I'm going to tell you about something mysterious type of galaxies that appeared in the last year or so, and an old problem of formation of cusp and core in galaxies. So this is the puzzle. Here is an ultra-diffuse galaxy. It is only 10 to the 8 solar luminosities compared to Andromeda here, but it's almost the same size, or roughly the same size, a few kpc. A very diffuse galaxy, very extended, a dwarf in luminosity, but a big galaxy in size. What is the origin of this? There are many ideas. There are three basic ideas. One, that a massive galaxy, a massive halo, failed to form stars. This may be in clusters, especially because you have tidal forces and so on. Some idea that Avilab and Amorisco suggested is simply you take a halo with low spin parameter or high spin parameter and you make a big galaxy. And what I'm going to focus on today is the idea that you take a small galaxy, a stellar system, and you puff it up because of supernova outflow, which appears in one of our papers here. So that's what I'm going to tell you today. I'm using simulations, the HAWC simulations, which are pairs of simulations, one with baryons and dark matter, the other one is dark matter only. So you can see the effect of baryons flying out of the galaxy. This simulation, among other things, reproduces the stellar mass-halo mass relation and other observations, like other cosmological simulation. We focus on the inner part of the halo of these galaxies. And these are typical UDGs that we get in those simulations. Edge on and face on, as you can see, they are puffy disks, and pretty much like the observation. In fact, if you look at color, effective radius, or surface brightness, the black are the simulated UDGs, and the red and blue are observed UDGs, and you see that pretty much simulations reproduce the observations. Let me show you one important thing. There is a very narrow mass range within which you form the UDGs. It's a halo mass of around 10 to the 11 solar mass, and stellar mass around 10 to the 8. The blue is UDGs, the gray is all the galaxies in our simulations, different galaxies, different mass. You see, strong tendency in a very narrow mass. The shape, the self-settiness is around 1, as you can see here, the blue compared to the others, but they are puffy. They are not flat disk with n equals 1. The spin is typical. If you look at the galaxy spin, you see high spin because it's an extended system. But if you look at the halo spin of those hosts, they are not much different from all the other usual distribution of halo spin. So at least in our simulations, the UDGs are not coming from particularly high halo spin. They do emerge because of star formation histories being very episodic for a long time. Those two are UDGs, star formation histories. Those are non-UDGs. They really finish forming stars early on. This guy continues episodically, and these episodes are responsible for the UDG. You see that the stellar profile evolves, and the dark matter profile, you form a core from a cusp at the same time that you form in a very extended UDG. So these are the same phenomena. It's n-body reaction, stars, dark matter, to removal of gas from the center. You can see that our galaxies have very flat cores. This is the slope of the density profile in the core compared to all the other galaxies in the simulations. And let me tell you about a simple model of how to do this very quickly. It's a dark matter response or the stellar response to sequence of inflow and outflow. The idea that you take a shell of dark matter or stars at a given hour encompassing a mass m in virial equilibrium, a mass m falls in or ejected out to the center instantly in this simple model. You can change it to adiabatic changes. In step one, you assume that the potential changes instantaneously while the kinetic energy is constant. So the total energy changes and you are removed from virial equilibrium. And then the idea is that you relax to the virial equilibrium while conserving energy. And then the radius of the shell encompassing mass m contracts or expands, depends on whether you have inflow or outflow. In this simple model, okay, this is the potential, this is the energy, this is the kinetic energy in virial equilibrium. You put in mass m, fractional mass f, and you, by this simple model, you get a final radius to the initial radius, scaled like a combination of f. Then you put outflow after the inflow with beta, a factor. If you have full outflow of everything, beta is 1, no outflow, beta is 0, and you get this expression. To a linear approximation, it has a first term in f, which is negative, and a second term in f, which is positive. And that's the key. Okay, for very small f and very strong feedback, the radius grows to second order in f with 2f squared. So you're going to get net expansion if beta is high or f is high, if you have a lot of outflow, and net contraction in the opposite case. This typically happens when supernova feedback is strong, below critical mass, halo of 10 to the 12, or 11.5, and this will happen, a contraction from massive galaxies, above 10 to the 11.5. Indeed, in the simulations, that's what we see. As a function of mass, really, from left to right, this is the mass within a given radius, 1% of the virial radius, in the hydro case versus the no hydro case. This is where supernova feedback works. What you see is nice expansion in a given mass range, intermediate mass range. We have strong feedback, so beta is 1, and these terms give you this nice expansion. If you are much more massive, you have contraction. Okay? You have more mass within a given radius, and this is because of the low beta and the weak feedback. So that this term wins, you have 1 minus f in this term. Here you have this term. Now, if you are too low mass, the feedback is so effective that it prevents accretion, and there is not much star formation. No star formation, no feedback from supernovae. So nothing much happened here. Now, you can do it a little better by assuming not shell by shell, but rather a whole potential profile, and you do the same thing, except that you need a functional form for the potential and the mass that's analytic, which we have developed, and you use this equation. Now this is not true anymore. You generalize this by taking into account the potential from the other shells. And this is what happened when you compare simulations to this model. These are 3 time steps. This is the initial profile of the stars or the dark matter. And this is the final profile after this time step. And the red is the model. So you see the model is doing very well, both when you have outflow and expansion and production of a core, or you have inflow and contraction and production of a cusp. So this is a very useful model to use, and let me conclude that UDGs and dark matter cores form naturally in simulations of field galaxies with strong supernova feedback. Through episodes of inflow and starbase and outflow, a narrow mass range is predicted for stellar mass and halo mass, and a simple toy model can match the simulations and give you very predictive things just using instant outflow and energy conservation. There are several open issues. Observations are going on to find more and more about the properties. There is some controversy about halo mass, in particular because there are many globular clusters found, and the number of globular clusters is known to be a proxy for halo mass. So we have to understand what's going on with the globular clusters. Everything I said was about field UDGs. You want to be able to make them also in clusters and see the environment dependence, will they survive tidal effect, and so on. And finally, the problem really for us in the simulations, we get these nice UDGs, but we don't get very compact dwarfs, which are observed. So the question now turns around, how do you produce compact dwarfs at the same narrow mass range? Is it when you have weaker feedback? Is it because those simulations had a very strong supernova feedback? I don't know. Thanks.
Is what is driving UDG formation. What are your predictions for the ratio of how commonly they should occur in clusters versus in the field? And also it seems from a recent paper from the Van Doken group that there's no tidal effects in the cluster UDGs, right? So
we have not studied cluster UDGs yet, so I believe this is an open question. We have only showed this in the field, and it's a real question of to what extent you expect the clusters to change the story. Okay, so stay tuned. What was the second question?
no.
Okay.
Any other? We need to move on. Thank you very much.
Thank you. I probably don't need this. My name's Dan Hooper. I will? Okay. As you wish. All right, my name's Dan Hooper. I'm at Fermilab at the University of Chicago. I'm giving the CFA colloquium later today. I'm going to talk today about the cosmic positron excess. You might have seen figures like this over the last, say, I guess it's been 9 years now since Pamela first announced the discovery. And this is the AMS measurements, which are much, much more detailed. Is there a pointer somewhere that I'm missing? Perfect. So at the time, there were proposed, shortly after the Pamela observations, 3 essential resolutions to this surprising observation. Basically, they came down to something exotic, like annihilating or decaying dark matter that are producing, through some sort of cascades, large fluxes of electrons and positrons. And then there were secondary models where you have cosmic ray accelerators like supernova remnants producing positrons in the acceleration environments, which then get reaccelerated before they escape the sources. That was a possibility. And then thirdly, another class of resolutions was that there was one or more nearby primary sources of E plus E minus pairs, and they account for the rapid climb in the positron flux and therefore positron fraction. So I'm going to focus here on pulsars and what we've recently learned about them from the HAWC telescope and the connection to this. So I've always kind of thought the pulsars were the likely resolution to this, but it was just my view, and it was pretty controversial at the time. The main question we had that weighed on the answer to the resolution of this question was what fraction of a given pulsar spin down power was likely to be transferred into the production of high energy pairs. There were papers, and you could find in the literature, that suggested that maybe tens of percents of their total energy budget went into these particles, but there were others that said it was 1 part in 10 to the 4, 10 to the 5, and without knowing this number, it was very hard to assess the likelihood that nearby pulsars were in fact responsible for this observed rise. So let's ask the question of which pulsars do we think are most likely to contribute significantly to the rising positron fraction. You can just solve the diffusion equation and get a clear answer. And it approximately corresponds to those pulsars that are about 100,000 or so years old and roughly located about 100 parsecs away from us. So those are the ones that are going to dominate the positron fraction, all else being equal. From these considerations, there are really two known pulsars that are good candidates for this sort of contribution. One is Geminga. It's just under 400,000 years old, at least its characteristic age is, and it's located about 250 parsecs from the solar system. And the next is BO656 plus 14, also known as Monogem. It's younger, but about the same distance. So these two are the ones we're going to focus on. I will point out, however, that there may also be pulsars in our neighborhood in this age that we don't know about simply because their radio beams aren't aligned in our direction. So it's been known for a long time, and here's just one example from some work I did with Ilias Cholis, that these pulsars, along with others in the halo, but predominantly these two, could dominate the positron fraction and explain the observed climb if on the order of 10 to 20% of their total energy budget goes into high energy pairs. All right, so Milagro detected very high energy emission. They reported a flux at 35 TeV from Geminga, and they also reported at the time tentative evidence that this emission was spatially extended. It didn't appear to be coming from the pulsar itself, but from an extended region a couple of degrees in radius. Very recently, the HAWC collaboration has confirmed this. They report a 2-degree extended radius, so here's Geminga. And in addition to that, they also report a flux from BO65614, shown here. They just happen to be in similar parts of the sky, and it has a similar spatial extension. In the past, BO65614 was not detected by Milagro or by Fermi. So this is an entirely new discovery in the gamma ray band. The spatial extension of these sources, so the fact that these are not point sources but a couple of degrees in radius, tells us that the emission doesn't originate from the pulsar but from the region surrounding the pulsar, several parsecs at least in extent. And this is almost certainly inverse Compton scattering. I don't think there's any other plausible explanation. And what's important about this observation is this allows us to measure the critically important and until now highly uncertain quantity, which is the fraction of these pulsars spin down power that's going into E plus E minus. So this provides a direct way to measure this important unknown parameter until now. All right, so we did that. So we took a given, we assumed some parameterization for the spectrum of injected pairs from Geminga, and we calculated the inverse Compton gamma ray spectrum, including all the Klein-Nishina corrections, and we used these measurements to constrain the parameterization, the parameters that describe the injected spectrum of pairs. And here's an example of two pretty good fits. Has a spectral index of either 1.5 or 1.9, and an exponential cutoff in the energy of the electrons and positrons at tens of TeV. You can see that these models do a pretty good job of explaining the emission observed by HAWC and by Milagro in each cases. And importantly, across all of the best fit models that we found that between 7 and 29% of the current spin down power had to be deposited in the pairs. And I told you before that we wanted something like 10 to 20% in order to explain the positron excess. So this was a very interesting number and very suggestive indeed. So this is the So this bottom line is what you'd predict from simple secondary production of positrons in the ISM. This is what our models predict should come from Gaminga alone. Okay, so you can see that they don't accommodate the entire excess flux, but you can see across the range of models that seem to agree with HAWC, a non-negligible contribution comes from Gaminga alone. And if we combine this with what we think the emission from monogem or BO656 plus 14 would look like, along with the smaller contributions from more distant and older pulsars, you can easily explain the entirety of the observed positron fraction with these sorts of objects. So in this particular plot, we made a couple of assumptions. We said that all of the pulsars inject pairs with the same efficiency. In other words, the same fraction of their spin-down power is going into pairs. We adopted a 4,000-year spin-down time scale and a birth rate of 2 new pulsars per century in the Milky Way. These numbers might not be exactly right, so these numbers can all move up and down by an order of 1 factor. But I think it's pretty clear from this information that we can reach this conclusion. So pulsars almost certainly provide the dominant contribution to the positron excess and quite plausibly can generate the entirety of the excess. So I'll just close with what I think is a cute popular science article that was written about this. This journalist thought that we had found something that was really uninteresting, namely that this doesn't seem to be coming from dark matter. I actually think it's pretty interesting to understand pulsars and in the high energy emission, the antimatter they create, but this is their particular take on it. So thanks. Yeah, it doesn't happen very often.
Must be right. Any questions to them?
Any hope for getting measurements of higher energy? Check the
Yeah, I mean, slightly, yes. So AMS will take data for a long time. With the accumulation of that data, those error bars will get smaller, and they'll be able to probably do 1 or 2 more error bars at higher energies. But I think you should have modest expectations for that with any planned or proposed experiment.
Thank you very much, Ben.
Sure.
Untangle all this. Okay, so I'm back talking about the Eagle simulations, and it's very tempting when you have a numerical simulation of the universe that includes the cooling of gas, the formation of stars, and the formation of black holes, to wonder what it would be like if we had a different universe around us. And in this particular project, we've been asking, what would happen if there were no cosmological constant in the universe? How would that affect the amount of stars formed in the universe? Okay, it's work that I'll be talking about is by Jaime Soshido, who's managed to get a little label over the top of him. Okay. So, what I want to look at in particular is the star formation history of the universe. This is a plot from Michel Furlong's paper comparing observational data. As we look back in time, we see a rise in the cosmic star formation rate out to about redshift 2, and above that, this rate declines. The Eagle simulations do a fairly good job of replicating that. If you shift this curve up by 0.2 dex, because we don't exactly fit the observed galaxy stellar mass function, it would go very neatly through the data points. So very interesting. What we can do, though, is we can now look at the origin of this shape. And in particular, I wanted to know whether this decline here was in some part due to the accelerated expansion of the universe. I mean, part of this decline is simply because the dynamical time of the universe is getting longer. Okay? But is there also an effect in here due to the cosmological constant? And the corollary of that is, could the cosmological constant be much larger without causing this decline to set in very rapidly and leave us with very little star formation in the present-day universe? Oh, I've only got 10 minutes, haven't I? Now, okay, so let's accelerate then. So there's lots of... so this paper should be on AstroPH tomorrow. It's presumably going to get lost in all these gravitational wave things, but never mind. That's just the way things go, I guess. Now, one problem trying to explain this paper to my colleagues is that we are not trying to invent a universe with no cosmological constant that also fits the observed cosmic microwave background. A present-day observer in this Einstein-de Sitter universe would not see the same cosmic microwave background, but the universe at very early times would be identical to the universe, our universe, when the universe was very young. And we use this to initialize the simulations that I'll show you later and look at the effects of this difference in expansion history. Okay, I can't resist the temptation to run into the future, so this gives you a little idea of what will happen to the difference in expansion factors. Present day, we're down here. We're going to run to about 20 billion years before we decide that we can't use the computer time to go hundreds of billions of years into the future. We don't actually need to. Okay, now the other interesting thing is how you parameterize this, and in contrast to the normal way of writing the Friedmann equation, it's useful to think of a time scale associated with matter, the normal Hubble time, and a time scale associated with the exponential expansion due to the cosmological constant. By writing things this way, you can also parameterize them explicitly so that the expansion factor here is it relative to the present-day expansion factor of our universe. So only our universe, the green curve, goes through 1 at 14 billion years. Okay, so let's see. Now, the interesting thing is you can take the Friedmann equation in this form and look at other things you can solve this. You can now write down the expansion factor as a function of these time scales. Looks pretty awful, but it turns out that you can do a very good series expansion of this. And, oh look, you pull out the Einstein-de Sitter part, and you have correction terms where these coefficients go to 0 very fast, and you're left with corrections dependent on the ratio of the time to the cosmological constant time. All very interesting, but there's no time to look at that. So you now can work out, I should have done this in 1991 when I was bright and able to do things quickly, because this just comes from the extended Press-Schechter theory. Basically, you can take the amplitude of the power spectrum, you can compute the growth rate of fluctuations, you can use Camilla's new work on the collapse rates of halos to then factor these in to compute the growth rate of halos for the two different universes. And because of this power law expansion is so great, you can actually write it down on a piece of paper, amazingly. All right, so that's very interesting. So we can go all the way to here, the growth rate of dark matter halos. Now, if you were at my other talk, you'll see we understand galaxy formation well enough for this. And basically, there's an efficiency of forming stars as a function of halo mass. And if you're in small halos, this rises rapidly with the halo mass. If you're in large halos, it declines rapidly, and leading to a peak. at singling out a particular halo mass. And the interpretation is this side it's due to supernovae, on this side it's due to black holes. Okay, so now combining this efficiency with the growth rate of halos, you can pick a particular halo mass, that's one of these curves here, and calculate its contribution to the cosmic star formation rate density on a sheet of paper. You can then add all those up. I had to use a computer to do that, but now you've got the cosmic star formation rate of the universe, and interestingly, there's hardly any difference in these dependent on the value of the cosmological constant. Because it enters in these formulas very weak power coefficients, although the growth rates are quite sensitive to the cosmological constant, there's a compensating effect, because in the Planck universe, with the presence of lambda, halos are rarer, therefore the growth rates of those halos are more sensitive to the change in the barrier in the Pressure formalism. These two effects largely cancel out and give you this curve being very insensitive to lambda. The reason this doesn't keep going is my old friend, black holes. Okay, and you see that neatly. Also, here's the analytic solution. How well does it work? I've got far too little time. So here you are. This is the analytic prediction. These are the small dependencies on lambda. We can compare that to what actually happens in the Eagle simulation. Remember, this approximation was all very simple just to get it on a sheet of paper. This is what actually happens. We're a little bit simplistic. This comes to the discussion we were having about high redshift halos this morning. But there's this decline is really very well described by that very simple model. Now, what you wanted to know in 1 minute is what happens in the future. Well, they just get a little bit different. But there's no kind of sudden moment where these two universes suddenly start forming stars at very different rates. Oh, so that was a bit boring, so let's do something more exciting. Let's have a universe with no black holes in it. See how important Einstein is. Well, that's a bit important, okay? So it gives you a little bit more star formation. This peak shifts across. But in Eagle, even the supernova are having some effect on suppressing the cooling in these relevant group scale halos. But the universe still has one surprise left, which people of my generation will love. What happens in the universe with no black holes into the future? Very good. And so what happens is the big clusters, supernovae, are not energetic enough to keep them hot. Eventually they overcome the energy injection from the star formation and they go cooling away like bilio and start filling up the star formation of the universe. And, you know, I'm looking, Avi, for a good name for this, you know, the universe reignites. So, yeah. Yes. So, where are we? Oh, and so the interesting thing is all the stars in the universe have already formed, regardless, lambda, no lambda. Lambda or no lambda makes very little difference to our universe. Thank you very much.
One difference is that if there is any intergalactic medium, it would never accrete with lambda. In an Einstein it's
yeah. Yeah, exactly. So you get these differences, but they're relatively small is the interesting factor. And before we did the project backwards, of course, and we did the simulation and went, what did we do wrong? Why didn't we see a big difference? You know, and then we ran into the future, still no difference. And then you go back and actually do the theoretical calculation. So very interesting. Thank you very much. Well, that's our cusp. Right. Okay. I've got to not leave the $100 connector behind. Oh, and I've got to take the mic off.
So, all right. Hello, everybody. My name is Lluis. I'm a PhD student in Norway. Similar weather than here, more or less, for now. At least I'm applying for postdocs now, so that's why I'm visiting. And thank you, Stasia, Avi, for hosting me these 2 or 3 days. I'm working on cosmology, Lyman alpha forest, quasar spectroscopy, metals, but also on galaxies, is reionization. And today I'm going to talk a bit about this. And I will talk about this extended emission, and what this extended emission or extended halos are is something like this. So here you see, and I will follow this color code, it's 3 colors, and this is what you see in these galaxies. This is at redshift 0 by the Lyman alpha reference sample team in my neighbors in Stockholm. And what you can see here is in green you see this UV continuum stellar radiation, non-ionizing. So basically where you see green, you are seeing stars. And then the blue is Lyman alpha, and the pinkish is H alpha radiation. So the common picture that happens here is sometimes you see that there is this extended blue thing or pink around the region where you see the stars here. However, redshift 0, there is a big variety, so sometimes this doesn't happen. However, now there is this fantastic instrument, MUSE. They have a lot of IFUs in a single instrument, and they can do super sensitive things. And it was reported in this Vysotsky paper last year, the observation of 26 Lyman alpha emitters between redshift 2 and 7. In all of them, they observe extended Lyman alpha emission beyond the stellar component. So this is the surface brightness with radial distance from the center, and you see that in red, the continuum, the UV that was green before, it's very compact. However, these blue data points are Lyman alpha, and it's much more extended. So this is something that happens almost in all star-forming galaxies at high redshift. So where this comes from, and well, the usual explanation is like, okay, you produce Lyman alpha with your stars, and because Lyman alpha can scatter and can travel away, you diffuse your Lyman alpha photons, and you see this extended emission. However, if you run your favorite radiative transfer code, you see that you have a hard time reproducing all the luminosity that is observed in the halo. So there are other possible mechanisms. And these possible mechanisms are here, and this is how they affect or contribute to any of these 3 transitions or radiations. So basically, we kind of explain in a paper we put a few months ago how you can disentangle what's the origin of these halos or this extended emission. So basically, you just need to look at if your UV or your H alpha is compact or extended, because they are affected by different mechanisms, so you can disentangle the thing. For instance, if you have extended UV, this traces star formation, so probably you have extended star formation in the circumgalactic medium on the galaxies. Ultra-faint dwarfs, cold gas accreted that forms stars, whatever can happen. If your UV is compact, then it's not stars, but if your H alpha is extended, this can be, for instance, fluorescence. Fluorescence here, I mean that you produce ionizing photons. These ionizing photons escape the stellar regions, and they interact with the neutral hydrogen in another part. Ionize, recombines, and you get H alpha or Lyman alpha. This will be important for the next slides. So we took a look at things. One was fluorescence. With accounting for fluorescence, we could not reproduce all the extended profiles. But then we thought, okay, what happens if you populate the circumgalactic medium or your galaxy halo with satellite galaxies or satellite star formation? I will not go too much into details. We can talk later if you want. But basically, you see here data points in magenta and cyan, and our favorite model using a nonlinear correlation function of Lyman alpha emitters and some radiative process parameters constrained by observations, we kind of did a pretty good job in reproducing this extended emission. There is a big scatter here. You can apply your escape fraction of photons, and that can vary a lot. But it looks like satellite galaxies, if they are there, they can explain part of the trick. And the thing is, these satellite galaxies will be very small. We cannot see them individually, but maybe they have something to do with this faint galaxy population that we need at very high redshift to reionize the universe. I will go to this in a second. How can we constrain this? Well, you just need to wait a couple of years, and if it's able to deploy when it will get to Lagrangian something point, then we can, I did some predictions for JWST, and well, this is the error bars on the detections, And well, it seems that at up to a 60 physical kiloparsec from the center, it should be possible to constrain pretty well the extended H-alpha emission with near-CAM imaging. Also the continuum. So again, continuum, H-alpha, Lyman alpha, we compare and we know what's producing this. More interestingly, let's go to redshift 6, and 6 because it's where I found data already available, but you can put it at redshift 8 or something like that, and then we can say something about reionization. And there are two key questions at reionization. Who or what kind of galaxies reionize the universe, if there were galaxies, or if it was galaxies, and what fraction of ionizing photons is produced by every type of galaxies. So let's do one simple analytical calculation. We take two models for the neutral gas around the galaxies, how the neutral gas distributes. These two models, one is Chakstadel outflowing model, and how the neutral gases distribute. This is the solid line. And then the dashed is based on Ali Ramati in the Eagle team, in the Eagle simulations. Also the neutral gas distribution around galaxies. All this at redshift 3, because at redshift 6 we have no idea how the CGM is. But we just use the same models to see what happens. From this neutral gas covering fraction, we can infer an escape fraction of ionizing photons. Our galaxy will be here, the ionizing photons will escape, but they will be reduced depending on this neutral gas. So basically the two models, one gives at the virial radius around 40% escape fraction of ionizing photons and the other 5%, just to parameterize our ignorance at this redshift. If we apply this to some data, we have our two models, and we apply these two models to some data. This is funny because this is one paper and this is another paper. These guys here use the stacking of 40 Lyman alpha emitters. And these guys here use the stacking of 400 Lyman alpha emitters. But it's the same Lyman alpha emitters. So this is a subsample of this. And in this case, there is a lot of extended emission in yellow. But here, they claim, no, there is no extended emission at all. So it's a bit contradictory. This is very difficult. It's not they don't know how to do the job. It's just because it's super difficult. It's super difficult to do stacking, account for the systematic, remove backgrounds and things that observers do, and I don't know very well. But it's difficult. So I just plug my two models here, trying to reproduce all the integrated luminosity. And well, this is what we get. You see that sometimes the error bars go crazy. 5.7 redshift, 6.6. And well, in general, we could say that it looks like these galaxies, which on average turn out to be bright, don't have a very large escape fraction. It's not super surprising. This is what we usually say for reionization. Bright galaxies never do the job. They produce ionizing photons, but they are not able to escape. So probably there is this faint galaxy population that I told before. So what I can do is do that trick that populate the halo with star formation, because these faint galaxies probably are clustered around massive objects. And well, I didn't tell you, but here I already put these green lines are the fluorescent from the central bright galaxy plus the curve from the satellites. But it's not very important. However, again, if we want to attack the faint galaxy thing better, we can go instead of Lyman alpha, which was before, to H alpha with JWST. This is my predictions. Sorry about this. I don't think we will be able to see anything even with JWST. This is 10 to the 5 second exposure. Yeah, nobody will never get that. Yeah, exactly. However, this is one galaxy. In the field of view, you can target 100 galaxies and you can stack. And you reduce by a factor 10 your noise. That's something else to consider. However, one single galaxy, we don't go beyond in the detection of 20 physical kiloparsecs. We are close to the PSF of the instrument, and it's difficult to disentangle between the two escape fraction models, and these are our satellites. But well, before these two Japanese teams had data from Subaru, and now with the Hyper Supreme Cam, Masami Uchi and these people are observing many more Lyman alpha emitters. They have 1,000 or something. So I'm just waiting for them to publish this in a correct way, so I can plug my models again, and maybe I can say something else. All right, so this model is nice, because we can constrain the escape fraction at reionization, and the presence of faint satellite galaxies clustered around more massive objects. This is actually what we want to do. Simulators in the room, please tell me something, apply my analytical models. And I have something more very nice that I need one more minute, but I don't know if, should I got? Okay. Can we do something else with this extended emission? Yes, we can do everything. This is like gravitational waves. We can attack everything. This month, 2 papers appeared on this, detecting the cosmic filaments in thermal Zundjaev-Zeldovich effect. 2 papers doing the same thing, and they are consistent with each other, which is much better than the Lyman alpha people. So basically, they stack pairs of galaxies. They put them together, they normalize, they stack a lot of galaxies, thermal Zundjaev-Zeldovich, and here what you see is the total image. Here, they model the halo of the galaxies, the signal from the galaxies, and then they subtract this from this. And this is the residual. So here, they claim that what we see is a cosmic filament glowing in thermal Zundjaev-Zeldovich effect. So the free electrons interacting with the CMB background and provoking this distortion. However, this is amazing, but they constrain the Y inverse Compton parameter, which depends on electron density and electron temperature. And it's like, okay, we constrain these 2 things together, but what happens? Well, if we go to our halos, again, and we target a super bright quasar, the luminosity of this quasar will go out to the halo and will scatter also with the hot gas and the free electrons, which is something that we really want to constrain because we don't see the warm, hot CGM of galaxies. X-ray is above, and when we go to absorption lines or something, we are below. So there is 10 to the 6, 10 to the 5, 10 to the 6 Kelvin that we cannot constrain. But Avi, actually, I think he was one of the first, Avi and Rashid Zundjaev, they put a paper on the radiation from this quasar will be scattered by Thomson scattering of the free electrons here. So basically what I did is just go to this guy's paper and I just put James Webb calculations, and it seems that it will be 30 minutes now. I think we can write a proposal. 30 minutes, we can constrain or we can detect the scattered emission from the quasar up to 100 physical kiloparsecs from the CGM of a quasar. I calculated what happens with dust. It doesn't matter if your quasar is bright enough and hot enough. What happens if you have nebular radiation, your PSF, Bremsstrahlung is negligible. So this is very nice. Why is very nice? Because this signal is just proportional to density. So we are constraining density directly here. If we can do this in the filaments, maybe we can break the degeneracy with the other guys, and maybe I hope this. I will put this. We should submit. It's submitted, but okay, it's not on archive yet. The other things are on archive. But when I put it, let's see if I have so much press thing that the filaments. That's it. Thank you very much. Yes. Yeah. That's right, yes. Yeah.
That's all for lunch.
Yes, my friend, the CMB guy. Oh, he is the French guy I told you. He's Ben. There is Anastasia, there is a microphone here.
Yeah, just leave it.
All right.
Nice.
Yeah, thanks. It's really stressful, 10 minutes. Super rushing. Yes. Ben, she's Anastasia. You have some CMB uninteresting stuff.
Yeah, no, I'm going to but
I'll see you later. Yeah.
haven't seen the paper yet. If I find it, I'll try to give it to you.
Yeah, no, that's really.
But it did take enough, yeah. That's a 3.6.
Yeah, but that's
It's actually, yeah, I haven't seen the paper.
Tomorrow morning at 7.
So the frequency of rushing doesn't diminish.
Oh, all right.
So now we show the
So you say I have different brushes, and I can tune the models up. They can compensate each other. That happens with black hole.
Joel, I don't know, Charlie, we were expecting you. Let me show you what you need to do over here, all right? So, basically, this is so you, when you can understand, you can come and go from here, right?
Oh, gotcha.
All right, so. I'm just gonna help him along. Yeah, we can do kind of like this, so if it doesn't go for you, it's really, but help this help.
Do it like that.
Just gonna have your
So what kind of you got to
All right. Yeah, that's it, buddy. That's cool. Thanks a lot.